Recording, and you are go.
Okay, so do you need to take a bio break for 5 minutes here? Or do you want me to get going? Say yes or no.
No.
Go ahead and roll with it.
Okay,
Roll
well,
on.
we'll try to go through. I won't try to keep you too long on this. I am going to have to start my screen sharing here, and I'm going to show you, my goodness, what do we got here? Oh, I can't do it that way. Well, I still have to do it that way. So we're going to share the screen, and then I'm going to share individual windows here in a minute for this. I need to get rid of some of this other stuff here. And we don't need this. We don't need my other email. We probably don't need this. All right, so what we're going to do today is we're going to look at some 6-meter beams, and we're going to use a software. You won't be able to see this, I already know. You're just not going to be able to see much of this. And I'm going to bring up my participant list and park it over on the side here someplace, just in case you need to raise your hand or something and get my attention. But
I'll watch for it too.
Okay, great. So basically what we're going to do here is we're going to use a software package called 4NEC2, which is freeware by a guy in the Netherlands called Arie de Vries. This has been around for quite a few years now. I think I started using this in 2003 perhaps. This, the package you download from him actually has the NEC 2D engine in it. And what did that do? Oh, I have a chat thing here. I'm not going to look at chat. So anyway, so what you're seeing here is a set of screens. This is a main screen. Now, when I start talking about these individual screens, I'm going to share them so they go full screen to you, so you can actually see what, what I'm talking about. So we're going to look at a couple of issues with 6-meter beams. One of them is matching them. As you have with most beams, you have matching issues, and I have some information around here on the floor I have to pick up to remind me to tell you about the matching aspect of it. There's two things. You have a classical beams, which are in the order of 12 ohms or 18 ohms, something like that. Then you have direct connected beams, which you can hook your 50 ohm coax directly up to. And so we're going to look at a couple of those. So I'm going to start with this A50 Cushcraft modified by W5WVO. And let me bring up the actual beam itself so that you can see it. I have to use the right mouse to do this. Let's see, we want the geometry window. All right, so you guys should be able to see this particular window that I have right here.
Yep, see it.
And what you got is I'm going to tilt it over a little bit. And I'm going to talk about some principles of antenna modeling. You want to lay out your geometries consistently, or you'll get yourself so confused that you'll get so frustrated that you'll just give up. So you'll notice that what I've done here is lay out the elements in the X direction. I've laid out the boom in the Y direction, and I've done the elevation in the Z direction. So in all the models I'm going to show you today, the elements are in X, the boom and position of those elements are in Y, and Z is the height above ground. Okay? Now, the other thing that we can look at, where's my 3D window? This is what I put in as my thing for the Zoom meeting. So this is giving you the actual pattern that this beam has. This beam also, and we're going to sweep this beam, but I wanted to show you this pattern. The problem that this pattern has is you notice these big bumps in the patterns. As I move this around, you can see the big bumps. So what do you suppose the impact of those big bumps in these classical Yagis are? Well, you pick up local noise sources like there's no tomorrow. And if you look at this, this is approximately 3 dB that you're amplifying your local noise source. For 6 meters, this is pretty bad because you really want, you do a lot of weak signal work on 6 meters. So if you have any local noise sources at all that get amplified, your ability to copy a weak signal that's in the direction your beam is pointing is pretty poor. So there's a branch of beams that are called low noise Yagis that I'm going to show you one model of that I'd like to overcome that. But a classical beam pattern is what we're showing here. So if you have a question, hold up your hand.
No questions.
Okay. So I'm
Oh,
going to go back.
Mark just raised his hand.
Okay, Mark.
I'm curious, did this all offset the radiation pattern at the axis versus the lobes of, or the elements of the antenna? It just caught me off guard. It usually doesn't it center it around the elements of the antenna?
Yes. Now you might ask me, why did you do this, Scott? I did that so you could actually see the antenna and you can see its pattern.
Okay, now I
All right.
understand. Yep.
That's why I did it this way. If I showed you the dipole model, it goes right through the middle and you see the donut. But I wanted you to actually be able to sort of get a feeling for the antenna and a feeling for the pattern. Now the pattern is the far field pattern, so it's not tied to the position of where the elements are on the picture.
Scott, we have another hand raised from Brendan, Katie's.
Hey, Brendan.
Hey there. If this is too difficult to answer, feel free to skip it. How does this compare to our 6 meter beam that we use at field day? It looks like a similar layout.
I didn't model the 6 meter beam at field day. There are some differences though. In all my antennas that I'll be showing you today, they all have insulated elements. That means they're not connected to the boom. Our 6 meter antenna at field day is connected to the boom. And you might ask a really difficult technical question, which is, who cares? Well, it turns out that the length of the elements and their position slightly on the boom shifts when you actually have it connected to the boom. The length of the elements tend to increase by about 40% of the boom diameter. So you have to build them and actually measure them to actually figure that. Whereas if I use an insulated elements, the boom doesn't have any substantial effect on the antenna nor the model for the antenna. So you generally can get exactly what you build exactly what you see in the model, and it works. Does that help?
Yes, thank you.
Okay, I'm going to move over to the main window here for a second.
And we have a question from Diego.
Hi, what software are you using for this simulation?
Diego, your audio is just.
It is really
screaming
awful.
out.
We're running 4NEC2. That's what I said.
Okay, now,
Yeah, we're running 4NEC2.
okay, I'm just gonna text it.
Okay.
Okay, so it's 4NEC2, but I'm using the NEC4D 4.2 engine, which you have to have a license for from the University of California. It produces a little bit better results for this. All right, so I'm going to, I want to show you, we're looking at a pattern here, far field pattern. So the way I got that was, and this guy should overlap enough for you to see it. Jim, can you see this?
Yes, the small generate. You
Yeah.
pulled that in.
Alrighty, good. So I slew far field pattern, and I want to do it at about, for all of it, because I really want to see horizontal and vertical. And I hit generate. Now, you'll notice over here, my pattern went away. In a second, I'll get it back. I'm going to show you this window first so you can see what I'm talking about. All right, in this window, which you should be seeing now, I have some options here along the right-hand side. What I had before was the multi-colored pattern. So that's what we were looking at. And I got that via doing the far field measurement. So we can see that this beam at 50.1 megahertz. How do I know it's 50.1? It's because over here in this box, 50.1 megahertz shows up. Okay. The other thing that we want to know about is what if we sweep that over, say, 50 to 50.8? This will give us our impedance across the whole spectrum here that I chose to sweep. And I've got to bring this dialog up so you can see this. So you will notice that our SWR is from 4.5 up to 20 SWR. And this happens because this beam impedance is about 10 ohms to 11 ohms. Okay. And so you have to match this to 50 ohms. And I'll talk about that in a minute. So this is a classical design. It's about 12 ohms. And you match it to 50, and then you get back into the 2-to-1 SWR range. Now, I could go over here and say I'm driving this with 12 ohms. So I think I can do that. Oh, well, maybe not at the moment. So in any case, this you match this with a matching network, and then it works fine. At field day, that field day 6-meter beam, we use a gamma match on it, and that's how we match it to feed the coax. So this is the reason I'm showing you this is because this is the classic beam, 5-element beam on 6 meters, and that is its pattern. Now I want to take you to another beam, and let's look at the G0 KSC optimized wideband Yagi. And what have I got here? I don't have it. So I need to generate the far field for this. So I'm going and doing that since you're looking at that diagram. Then I should be able to put the pattern up. And can you guys now see the pattern? So this pattern looks real similar to the classical Yagi that we looked at. But this is called an OWA Yagi, and it's designed to have a little bit better wideband performance.
Sam has his hand up.
Yes.
Are those true nulls?
You mean in the, just a second, let me get out of this. I got something blocking. Yes, there are true nulls in this pattern. That's generally right off the ends of the elements, right?
That would make sense.
Okay, just like there are in dipoles. Let's see, and I am presenting this one, right? Yep. All right, so let's go back, and I want to go back over here. And what I want to do is do a frequency sweep on this guy out to 50.8. Now, I have to get rid of this and bring this up and bring, we tried this earlier, so we know that you'll be able to see it if I do what I just did. All right, this is also driven at 50 ohms. But you'll notice that even though the pattern was real similar between these two antennas, one of them had an impedance of about 11 ohms, and this one has an impedance of around 50 ohms. So what gives? Anyone have an idea? Or should I just tell you? By controlling the spacing of the driven element and the reflector and the first director, you can cause the impedance match to come down or to change to be something that's compatible with 50 ohms. So that's how they did that. Now, what is our gain here? Gain is about 10.5. So that's a little less than what we had in that other antenna, which was close to 11. And the front to back is still pretty good. And the front to rear, all right, do you know what front to back is? Front to back is, let me show you. Since we did this as a frequency sweep, so you're only going to see it, you're not going to see the full donut. The front to back is from here, the end node, to the front node. And whatever that delta is the front to back. Front to rear is looking at these nodes. I'm not sure I can get this any better for that. So there are two numbers you care about: front to rear, front to back ratio. And that's what it looks like. So those big little side lobes really cut down on the gain of the antenna and also introduce the noise source, the noise ability to pick up the noise. Excuse me. So let's go back over here. I want to pick a third beam. Goodness. Drink a little coffee here. Far field. And this is LFA Yagi, which I'll explain in a minute. It'll be pretty easy to see. Let's look at the pattern again. Now you notice this pattern is quite a bit different. You don't have that big lumpiness that was in this part at the axis that you had in the others. Now, why is that? Well, look at how it's driven.
Yeah.
Here you have basically a folded dipole driven element in this antenna. It's about the same amount of gain as the OWA antenna, but it has less ability to pick in close-in noise than that other antenna. So I tend to like these a lot. I have one. They're really hard to model though. And I can talk about that in a second. Let me bring this guy up. Okay, where is my efficiency? All right, you see this efficiency number here, 98.43. That says for every 1 watt or 100 watts going in to this antenna, 98.43 watts are radiated. The rest are heating up stuff in the antenna. Some of this is due to the aluminum of the antenna itself, and some of this is due to the modeling program modeling that folded dipole driven element. I see Mark's hand up. Go ahead.
Did, when you did this loop feed point, did that constrict the broadbandness of the antenna?
Well, why don't we just go run that thing and look at it? Here we go, 50 to 50.8. And I'll bring up that window. Doesn't look like it.
Well, now you have 2 points, which I'd kind of expect.
Well, I actually have 2 things, but this is still not a problem. The red line down at the bottom is not a problem. you want to look at your SWR up here. And the SWR is pretty flat for this entire frequency range. Now let's take a look at the gain. Did the gain go wonky on us? Yeah, the gain went down just a teeny bit at the edge. Front to back, just a little, 5 dB. Front to
Yeah.
rear. Or
Dan has a question too.
yeah, go ahead, Dan.
Like to figure out how to unmute here. I got too many screens going on. Sorry about that. That's a really interesting antenna. First of all, can you email me those models? Because I play with 4.2 NEC all the time myself. That's how I designed my 20-meter beam in the backyard. You have really high SWR on the first one, where it was just a basic dipole, and now you did the folded dipole, and the SWR just went down to 1.0, 1.5 at worst case scenario.
Well, that's also true on the OWA. Remember, these are designed to be direct fed by 50 ohms.
Right.
Where the first one I showed is your classical Yagi at 12 ohms.
At 12 ohms, okay.
Which requires a matching network.
Okay, so that's what was missing. I was wondering if, because I noticed the reflector was really close, and you had those lobes coming out to, get my camera here, you had those lobes coming out to the top. Would changing the spacing of the reflector also affect those lobes?
Yes,
Bring them down.
that's how these antennas accomplish the removal, this particular antenna, the LFA. That is one of the reasons why you have very good lobe control, is the placement of the actual elements is very precise to take out those lobes.
Al has a
The best
question.
the best website to go that has all of this information on it is G0KSC.
Kilo Foxtrot Zebra?
Kilo Sierra Charlie.
Kilo Sierra Charlie.
Golf 0 Kilo Sierra Charlie. Although this is my model for his antenna. So since you asked me about the actual model, I'm going to show you something in the NEC editor.
Scott, Hal has a question too.
Okay, hold on just a second. Okay, Hal.
Yeah, I'm muted. Yeah, the LFA antennas are very popular on 6 meters moonbound, and for all the reasons that you have identified, reducing the noise and stuff like that. And it's very broad there, looking at your broadness of the antenna. The most usable frequencies that we use on 6 meters is like 50.0 up to about a little over 50.3, probably 50.4. So it's a very broad and very nice to cover the entire 6 meter band that's usable for single sideband weak signal work. So nice antenna. You can model me a nice 7 element and send me the directions anytime.
Yeah, the G0KSC site has that information fully for a wide range of LFA antennas.
Yeah, I've seen them.
And he sells his via Innova, which is a UK company, but they will ship it from the US. All right, so I want to show you a little bit more of this model. This is directly off of the G0KSC site. These are the element diameters. We are in meters. Okay, so 13 millimeters corresponds to our half-inch aluminum that we get here. These are the RPs, DE1P, DE2P, DE1P, DE2P, DE3P are the actual locations of the elements along the boom in meters. So the boom length is 4.3 meters, so 14 feet, 15 feet, something like that. Nice size antenna, definitely manageable. Okay, so the R, DE1, DE2, D1, D2, D3 are all about the lengths of the elements. So these are the actual lengths of the elements in meters for each of the elements, and this came right off of the G0 KSC site.
Dan has a question.
Yeah.
Oh, I just that. Oh, am I unmuted here? Good. Yes, I am. Too many screens because I'm trying following along here, calculating. Something earlier you said about the size of the aluminum and everything like that makes an effect. If I was to build something like that, because I like to build antennas, and I did it. I got a couple of Yagis I'm tinkering with right now. I get those old school TV antennas, the really big ones, and repurpose that aluminum. How would that work with this model here?
If you know you probably can't use this directly. I'm just telling you. G0 KSC says you can't do that without a lot of work. You won't get the same pattern.
Okay.
This is a highly optimized antenna.
What aluminum is it using?
It's using this probably a 6061 T6 at 13 millimeters,
Okay.
or a half an inch.
A half-inch hollow?
Half-inch hollow. Now, the reason you use a half an inch is for that folded dipole. You need to insert the end items in there. So that's 3/8 inch tubing.
Yeah.
And you bend them and stick them in. And that makes your whole folded dipole for your driven element.
Okay.
So these
Cindy-
are actually not hard to build. There's plenty of videos on YouTube of folks that have built these that are really nice. Like, like Hal said, these are real popular. But this is why I use 4NEC2 for a lot of stuff is because I can parameterize like this.
Simeon has the clapping hand symbol. Are you clapping or are you looking for a question? Okay.
So SPM. So SPM here is segments per meter. It's real important to segment your antennas properly. I just cannot overemphasize this. You need to do a couple of tests, and I'm not showing you this. I'm not showing you much of this today, to ensure that you have a valid model. If you don't do those tests, who knows where your model is valid? Average gain test is one of them. Convergence test is the other. Now, 4NEC2 will help you with a couple of those. But anyway, let me, these were the symbols right off the G0 KSC. Now you see my geometry here. Here's my geometry. The number of segments is the delta distance times segments per meter. And notice that my dimensions are in half of an element dimensions. This is because it's usually easier to model it like you see here, minus R, RP, which is the position of the reflector, and 10 meters was how I flew the antenna to keep it out of the pattern. And it goes to R, RP, and 10. So that's a flat dipole of 2 times R in length. And so there you go. You can see how I did that. And then these are the diameters of the various elements. radius. Remember, this wants radius, not diameters. Okay, where did we drive this? Well, we saw in the diagram a little red circle. So the way this is done is tag number 2, which is in the geometry over here, tag number 2, which is the driven element item, part of that loop that's closest to the reflector. And you're going to do it at the driven element 1 center length, right? So that's the segment. And then we're going to do real and imaginary magnitude of 1.
What's SPM again?
SPM stands for segments per meter. You want to allow that to be controlled. Now this says aluminum 832. You could change this to whatever they have. So that happens to be the one that they have. I could change it to T6 if I wanted to from that drop down. Okay, this is our frequency settings for this. We're doing free space. I don't think I have any other things here nor comments. But basically, by building up a model that's parameterized, you're able to look at this a little easier. So let's look at, the LFA is my favorite, but let's look at the classical model. Let's see here. There we go. I'm back sharing again. Let's look at that classical A50. This is based on a Cushcraft design. And let's bring up the this guy, which you can't see yet, but you will be soon. Okay, so this one has a fairly similar, except that if you look down here at the bottom, it says inches. So this antenna is modeled in inches, not in meters. Now the NEC kernel itself is only in meters. So what this did is this added a scaling card to the deck for NEC that corrects the way you're doing it. So these element dimensions are 3/4 inch and 5/8. And these are the positions: 0, 26 and 7/8 inches, 64 and 5/8, 140 and 3/8, 206. Those are the positions for all the elements. Then you have driven element is that length over 2. And then I added a height parameter here so I can fly the thing over, you know, if I'll show you in a minute why that I might want to do that. So make the Z direction be the height. This is driven at tag 4, right in the middle. All right, so there are 25 segments. Notice this is not parameterized. This is a model I got from someone else. It's not parameterized. I would prefer it to be parameterized. So 1/2, the center segment number of this is 13. So that's why this is here. Is we're driven at 13, that looks the same. Frequency 50.1. What else did you want to see about this classical? Let me put this guy up. Alrighty, so on this guy, pretty classical 6-meter Yagi. Now, this is not the same as the Coachcraft A50. This is the one that is expanded. So let me see whether I have that document here. I did have at one point. Huh. Well, sorry guys. Oh, here it is. All right, so I'll share this out so that you can see where I got this. So this is improving the Coachcraft A50 5S 6-meter Yagi with extended boom and a little optimized design. So he has a nice article here. I don't know where this came out of, but clearly you can download this from the web someplace. And he gives all of his discussion about how to construct the elements and all that. And his gamma match network and everything else that he needed. So that's a good thing.
Did the gamma match kind of give the same improvement as the loop feed?
The gamma match itself is not an improvement. It is a mitigation to having such a low impedance Yagi. The actual gamma match causes pattern issues with the antenna itself because you are effectively moving the feed point off center of the driven element. Now, we usually don't care too much about that. We want it to match, right?
Yeah, but you got it offset on that side that it's matched on. You tend to.
Now, on the direct fed antennas, I see Sam's hand just a second. On the direct antennas, you don't need this match because you're gonna just use a little choke balun and connect up the 50 ohm coax right to it. All right, Sam.
Do you use a choke balun or a 4-to-1 balun?
On this one, you don't use either because this design matches the 12 ohms to 50 via this gamma match network.
Could you substitute a balun for the gamma match?
Not at 12 ohms. Okay. The actual thing that will match the 12 ohm Yagi is called the DK7 ZB match. DK Delta Kilo 7 Zulu Bravo match for Yagis. And it uses 2 parallel coaxial loops to match the antenna. This is a very popular match for 2 meters. I probably have 2 antennas down in the garage that have this match on it. So I would recommend that you look that up as the way to match instead of using a gamma match. But we do use gamma matches all the time. For the direct fed antennas, let me get us back over to the right spot. Let me go to, where am I going? I'm going to here. All right. Let me bring up either one of these OWA. I'll bring up the OWA one. Okay. Now, let's frequency sweep that puppy again. And then I need to bring up the frequency sweep window. And this matches to 50 ohms. This particular antenna, it goes 2 to 1 out here, but like, 50 to 50.4, its gain is fine on this. The big problem I have is the pattern of it, the noise of the pattern. I could show you part of that pattern over in this window right here without having to go to 3D. I hope. Hopefully it's showing. Just a second.
When that goes through a minimum, does it change, does it flip the phase 180?
Which minimum?
The nulls, those aren't true minimums there.
No, they're not. They're not. You'd have to look at the actual output file from the modeling program to answer the question about what happens at those points. Up here in the main 4NEC2 window, I have the ability to go into here and type F8. Actually, I should do it. I need to do a far field first before I do this. Okay, so we generated the far field. Now, if I hit F8, I should get, yeah, maybe not. Maybe I have to do it over here to get it. View. Nope. Supposed to be. Huh. All right, I don't see the window I was looking for here, but one of the configurations on this allows you to go look at the actual output. Like, is it here? Oh, that's the input. Where's my output? Yeah, I'm not doing well here. So anyway, there is a way of getting the output to show up, and then you can look at individual points and figure out what happens at those points. So here's the multicolor again for this antenna. The other thing that I have the ability to do is to show you the currents. This is why I fly the antenna separate from the pattern, is so I can show you the currents. So the element that has the most current is the first director, as you can see in this. So I have a couple of other things I could look at. I could look at segments. Now this is going to be a real problem to look at with this view because I'll have to zoom in like there's no tomorrow. But let's see where I can get it to go. Let's get rid of that.
Resolution of the display won't quite let us see it.
Yeah, hold on a second. I'm going to hide the pattern. Then I'm going to zoom it in. Zoom it out. Put this guy right here, I hope. All right, there you go. Now what you're looking at here is each of the segments in this model. Okay, so why do we care? That's always a good question. Why do we care?
Lost your presentation. There you go.
Yeah, I'm back in. I have to get this set up. All right, so let's do another thing that 4NEC2 will do for us to show you why we care. I'm going to show you this optimizer dialog. Okay, hopefully you guys can see that. And I'm optimizing for SWR. I'm not going to optimize for this guy, for the impedance. I'm going to optimize for SWR. But what I really want to do is do a convergence test on this antenna. Now, this is one of the tests you got to do to ensure that your model is okay. So we're looking straight down the antenna. We're going to look at total gain. We're going to do 8 steps. And that's 8 different segmentation steps. So this took the base model, which had, you know, number per segments, maybe number per meter of 15 or something. And this is going to go a lot more. So as you get more and more segments, it takes longer and longer to compute. So you can see that last 2000 segment run took what, 5 seconds to run? All right, so let's look at our SWR here. Look, the SWR didn't change a lot. Okay, the gain didn't change a whole lot. The front to back, front to rear didn't change a whole lot. And the impedance didn't change a whole lot. So I'm really happy with the base segmentation that this model has, because we don't show any major changes in the metrics of the antenna when we increase the number of segments to astronomical amounts.
So that's a QC check then.
You betcha. That says this model is good. All right, so let me bring up another thing that we should probably do. I think it's over in the main dialog again. And I have to close out this. All right, the other guy is do a far field pattern and run the average gain test on this. So let's just take a look. All right, and it just told me that wiring ground losses are set to 0 for this. So it did it. Okay. So you'll notice that we have efficiency of 100% now for this antenna. And the reason is we removed all the losses from the elements, and then we were able to get out the same amount of power as we put in. So again, this is saying that the quality of the model is good. Okay, so let me show you one more problem with the LFA. We want to do that same average gain test on the LFA. It's going to tell me that it's setting the losses to 0, and it still told me 100%. Well, that's unbelievable. But, here we go. That's more believable. This says that my average gain is 0.02 dB more than I would expect. So this model is a little funky, and I'll show you why it's funky in a minute. But let me go back, since I found that the thing. Let's do the OWA again and look at that same number for this average gain test. Go. All right, notice the average gain test results for this antenna is 1. That means there were no funkiness in the model that would cause losses. But we didn't see that in the LFA. And I'm going to run it again. And we're doing this far field average gain test. Now, 0.02 dB doesn't bug me. If you try to model, say, a log periodic or something like that, you're going to get a lot more issues than this has. But why does it happen? Why? So let's bring it up and let's look at the antenna again. And I want to bring up the segments, just like we saw before. And rotate so we get to look at the segments. Now the other thing, I may just try to blow this up. Oh yeah, now we're getting there. Okay, so the problem happens in these type of antenna drive systems when you have, are you seeing this screen? Let me make sure I'm showing you the right thing.
We're seeing the main
right
settings.
All right, let's show you the right thing.
There we go.
All
now
right.
You can see the segments.
All right, so I brought up the segments and you can see the segments here. The problem that all of these modeling software has is when you put sharp bends in your models. None of them deal with it very well. 4NEC 2 version 4.2 deals with it pretty well. NEC 2D doesn't deal with this at all. But, and you would end up, if I ran the NEC2 kernel on this, I might have, 2 or 3 dB loss. So the model wouldn't work very well. But anyway, so it happens because of these. So how do you compensate for that? Well, you carefully place these segments so that the distance is always the same around these corners. So the distance from this segment to this segment is the same. This model doesn't have that. You can see here that this segment, let me pull it back, this segment right here is the same length as this segment, but if you look at it, it's not the same length as this segment in the vertical direction. All right, so this is why we're seeing a failure in the average gain test. If I wanted to really model this and build it from my model, I'm going to solve that by changing the segmentation of the driven element. So that I know that the model, but 0.02 dB is not a big deal, right? Isn't that what it was? Yeah, 0.02 dB, not a big deal. The model is still good. All right, do you want me to show you one more thing? Or you guys about had enough?
I'm okay. I'm going strong.
We're
Go for
running this. We're running this with a Z of 1 wavelength.
I'm over. Let's actually look at the actual the model and make sure that we understand what we're modeling here. I want the geometry window up for this guy if it will show it to me. Oh, I see. I'm causing trouble. I'm projecting this window and I should be projecting this other window. Now this is a different beam, but we should decide what we want to do with it. Okay, so this particular thing is custom in millimeters. This model is in millimeters. All right, so the height is 10 meters for this antenna. Let me get you that. Why isn't it showing me? It says it's projecting it, but I'm not seeing the little green dot around it. But it says this is 10 meters high. But what are we doing about frequency and ground? Well, we're looking at free space. So we don't care about the height because we're in free space. But we'll go back to one of those other models and put a real ground under it, and we'll put a real height on it and take a look at it. So this is a 7-element beam that I'm just showing. And I need to switch to geometry view. So there's a 7-element 6-meter, and this is G6 CQM, one of the G6 CQM designs. Let's do the far field pattern of it. That way I can show you what it looks like. Oops, I did average gain test. Let's shut that off. All right, now I'm going to put up the screen so we can go look at the pattern. So what would you say about this pattern? I would say it's real similar to the other classical Yagis that we looked at. It has these dimples on here. So this would not be what I would think of as a low noise Yagi. It has 11.1 dB gain. The other was about 10.6 for 5 elements. This is more than 5 elements. 6 elements. Okay, so let's go back. Let me go back to that to answer Hal's question. All right, we're going to load up the LFA, and let's go look at its geometry. Let's see, I need to do the editor, and then let me bring up that window for you. All right, so the height here is 10 meters. Hal, what would you like for a height? He may have had to leave us.
Yeah, he took off just a little bit back here.
Oh, do something real. You know, real height for 6 meters doesn't need to be that high technically, but where would somebody typically put it? On their roof.
Well, here's what I would do is I would do HT equals 10.
No, that's a minus sign.
Did I hit the minus? Equal 10. Thank you. You guys get to see it bigger than I do. Then I'm going to do HT here. And I'm going to right click on this and say, come on. Thank you. And then I should be able to right click on this and say copy. And then I should be able to take this whole column and say make same value. Okay. And I should be able to do that over here.
That's
make
cool.
Same value. And we want HT. Okay. So now we have the ability, I'm going to save it out.
That was worth the presentation right there.
Okay. So now let's go fly this antenna. So let's make sure that the pattern still looks like what we expect. And I need to bring up this so that you can see it.
So Hal, really quick, when you said HT is 10, 10 feet?
10 meters.
10 meters, okay, just checking.
That's what it had before. So I just kept it. Now we're looking at the pattern. This is the same pattern we had before. Now let's go add a ground to this guy. And then let's model the antenna over various heights above ground. Let's do that real quick. Because I added that, the height to be controllable, that allows me to do it real easily. So the first thing we're going to do is we're going to go over to this dialog, which is here. And we're going to change the ground to be, how about real ground? Okay. Okay. So I have the ability to do that. Now, with that, I have the ability to select the type of ground. So I want to do average. All right, that's 13 dielectric constant and 0.005 conductivity. That is not good for us. We need to be about 15, but I don't know where is good. 17, that's too good. That's too bad. That's too bad. That's too bad. So I'm just going to leave it where it was. On average. All right, so we're going to use average for that, and now we're going to compute the far field pattern average ground at 10 meters. And we're going to look at the pattern. Okay. Ooh, something happened, didn't it?
That's
So
what I expected. That's exactly what I expected.
Right. So we can zoom it in. I can make the pattern be a little larger here, although you guys are seeing it just fine.
Now you see how a glide slope works.
Yep. Now, these are the nodes for that. So the biggest node is 15.7 dVi. There was coupling with the ground. Now let's actually go look at this antenna as we fly it. We want to fly it, so I need to bring up the optimization dialog. I have to probably close something to do that. Let me see here. Yeah, I have to close the geometry section in order to do this. All right, I need to bring up the optimization dialog and share that out. Optimization. All right, so what we want to do is we want to, are you guys seeing that? It's not green box, there it is. All right, I want to sweep the height. There's my height. So let's, it's saying 5 meters. So that would be 20 feet to 20 meters. Is that a good thing to sweep for real world stuff?
Yep.
Yeah.
Okay, so let's go sweep it. Oop, invalid property value. I did something bad here. Did I crash the software too? I did.
Get what you pay for.
That's what I get. I did something that I shouldn't have done here somehow. Let me bring that back up. I don't have this thing crash very often on me, by the way. And this is a crash in the optimizer. I'll present this in a second. I want to see where this will fail again. All right. So I'm going to show you in a second as soon as it comes back and I can share the screen. Where is my optimizer window? There it is. All right. So it must have corrupted memory or something because I was able to do it at the same time. So here you go. These are the heights over here on the right of the antenna. These are the SWRs of the antenna. They didn't change much. The gain changed a little bit, and this is very worrying, isn't it? At 11 meters, the gain sort of went to crap on this antenna at this particular theta. Okay, the theta is 75. Now, if we look at, we could sweep this in degrees. As soon as you find out where these guys are, the actual pattern nodes, let me show you what I'm pointing at. All right, these pattern nodes are at a certain degree. We're looking at 75. So clearly the pattern shifted to move higher or lower than the 75-degree theta. Okay, and that's why over here it shows this minus 0.26 dB. Whereas if you look at the heights where the pattern hasn't shifted that much, we're still all in about the 15 dB gain. Front to back is fairly similar for this. Front to rear probably changed at that one bad one. The impedance didn't change. So someone was asking about, in a real world situation, this antenna isn't affected much.
Now that 0.26 gain is probably as it goes through the first null.
Yeah, we could actually do this. This is at 11 meters height. So let me show you how to do that. So we go over and we go back to, oh, I have to close this. So I have to close this one. So we want to do 11 meters in height. So we go and edit the model, change HT over here to be 11, and run the model. Okay, so that's what I'm doing right now, and then I'm going to show it to you. All I'm doing is a far field pattern at 11 meters. Okay, so as Sam expects, we're going to look at it. So we went into the null, as Sam said. Can you see that? Yep. So that's why it went funky there, is because we don't normally have a node now at 75 degrees anymore.
I might remind people that in the basic geometry, a horizontally polarized antenna behaves as a cosine function, so you have nothing at the horizon.
By the way, here's your the way it looks as you're looking down at the antenna beam in the horizontal plane. Now, I don't know what height this is. Max gain phi is 90. Now, I think we actually have the ability to change this. Yeah, so that phi is directly in line with the boom. But this is the vertical plane. This shows us all of the junk in the antennas. All right, did I answer the question about the heights?
You did for me, but remember, I've got some background with glide slopes, so this makes a lot of sense to me.
Okay. All right, so did I have anything else I wanted to show you? Oh yeah, I have one more thing to show you. So you decide you're going to build one of these guys. Is it safe to build? So I'm going to go back and reshare I'm going to resume the sharing. I don't know why it paused. Now I'm going to show you something else. So I'm going to share the entire screen. And I'm going to get rid of some of these other dialogues and other crap that's on here. Do I want to exit 4NEC2? Yes. All right, what I want to do is show you that OWA Yagi and a piece of software called Yagi Optimizer. And I'm going to skip the wizard because I'm going to load up one of my models. And I think this thing stays to that same. There we go. All right, so you guys should be with me now. And I need to load up. Hold it a minute. Just a second. Yes, I want to exit without saving. So let me see how I can get that guy back. I know that you're not seeing me now, but at least maybe you are. Okay. So I need to load up this other's piece of software, and I have to find the right place to load it. I do not want the wizard. Thank you. I do not want this. I want this. I want this. I want something other than what I've got here. Here we go. I want to open up. All right, so I'm going to share this, the window again, so you guys will be able to see it. So, all right, so this is that OWA that we looked at for the 6 meter. This is the actual model. These are the actual real elements for this. So I could go, you're seeing the overview. So let's go into the design window for that initial element. I'm in element 1. I have a 0.5 inch diameter tubing with this 0.058 wall thickness. I have an exposed length of this length in inches. I'm using 6061 T6, which is 37,000 structural strength off of the site. I'm trying to look at the stress at 100 miles an hour on this element. I'm using EIA 222-F, which is the tough guy. And I'm at 100 feet. So this is pretty bad. Bad conditions for that. And the guy still is fine at 100 miles an hour wind at 100 foot height. You can see that because the stress PSI here is less than this material stress. Now, another option I have is the ability to click this little button here. And this says this will go up to 100.5 miles per hour for it tricks. So this is right on the edge. Let's go to the next element, which is the driven element for this design. We see that it's the same tubing. Exposed length is different, PSI is different, the stress is different. At the maximum for this element is 102.6 miles an hour, which is pretty good. Let's go to the first director. First director is exposed length 54 inches, same thing. At 100 miles an hour, it's fine. At it maxes out at 108.1. So I think you get the idea. We'll go to the other director. This one's shorter. So it doesn't even have 30,000. So it's 110.4 that it can handle without structural failure. Okay, for the final one, 113. So this gives you the idea that if you built this antenna, and I have to talk about the boom. So let's talk about the boom. And it popped up a different window, so I got to give you the boom window. Okay, the boom on this I did with 2-inch rectangular aluminum. At 0.125 wall thickness. You can get these at Online Metals, whatever you want. And I split this thing at the center so that that's where we would put the plate, the mounting plate to mount it to the mast, the boom to the mast. Now we have the ability in this dialogue to move the mount point differently along here and look at the stress. But if you look at this stress, there's no problem at 100 miles an hour with this boom at all. In fact, the boom will do 200 miles an hour before you run into problems. So the boom is not a problem, and the elements were not a problem at 100 miles an hour. The recommendation for our part of the US is 90 miles an hour. So these are all fine for putting up. Now, if you were over close to the coast, up in the Skagit, you will hit those 90-mile-an-hour winds. It's fairly common. I crank my tower down here when it gets above 55 in Puget Sound area. But all of my stuff is good for 100 miles an hour, everything up on the tower. Any questions on this? This is available from DX Engineering. Now, it will not model the loop thread array properly because it only handles straight elements. But it's still good enough. Okay, folks, I'm done, unless you have questions. I could show something from the net the other night, the technical net, but I don't know where I really want to show it. Let's see where I can find CPOLs. Okay, people are asking on the net, how many radials do I need to do things? And everybody had an opinion. Well, you could just model it. This right here is basically a crank IR. Let me bring up the one of the windows so you can see what it actually is. Where the heck is it? It's this guy. All right, I want to. There it is. Okay. So basically, what we have here, and I don't know why I'm screwed up like that. There we go. I basically have two wires. I have one that is the vertical portion that's about a little less than a quarter wavelength, and I have a radial, the counterpoise, which is a quarter wavelength. Height is 1 meter, and I have 51 segments per meter in this model. So there's the geometry for it. Now we can look at the pattern far field for this little guy. And you're going to see something you may not expect, although you might expect it. I'm going to share you as soon as I bring it up. I get this window out of the way. I'm going to share you this, and that way we can look at the bluing pattern on this antenna. Okay, so there you go. How come it's not going to allow me to get a pattern? There we go. Oh, it's not going to let me get a pattern. I must have done something funky. Did I do something funky? Far field pattern, generate. All right, now I got it. All right, so people were saying, wow, that counterpoise, it just causes the actual shape of the radiation pattern to change. Wow, that's interesting. This is over real ground, by the way. Let's change this model back to free space and run it again. Since this is really what folks probably thought. All right, so the pattern, can you see the pattern?
Yes.
All right, so you'll notice that it is tilted in the direction of the counterpoise. So this is what people were saying. Oh yeah, the pattern is tilted in the direction of that counterpoise. Well, my point is that counterpoise is only 2 or 3 foot above ground. So really, you have to model this correctly by using the ground, which is why I did this. Let me get this, I'll get the real ground back, and moderate. And remodel it again so you guys can see it. Alrighty, so that doesn't look very tilted, does it? So I'll just tell you, single radials are sort of worthless. Even in the crank IR, the reason that the crank IR is a little different is they off-center feed this dipole. Now here I split the dipole sort of in the middle here, and I didn't off-center fit it. I didn't make the top section, can you see my mouse when I'm moving it? I didn't make the top section be much different than the bottom section. But in the crank IR, they move this location for the feed point and the vertical portion to be off center fed. And that will affect the pattern a little bit, but I didn't model it. And this is at 1 meter wavelength. It doesn't matter what frequency you're doing. I heard opinions of radials for 10 meters, radials for 2 meters, blah, blah, blah. If you do the model, you'll find out that it doesn't really matter the frequency. And the only reason it doesn't matter is because the surface of the Earth is isotropic. Okay, so it doesn't have frequency dependent characteristics. But anyway, there's you crank IR gets about 4.85 dB high. And it fed at SWR's 1.05 at what I did at my model here. Okay, so that's it.
Well, Scott, that was awesome.
Well, you want to talk about real counterpoises. Back in the old days when I used to help take care of a 3-tower AM broadcast station with a single tower daytime and 3 towers at night. Each antenna was 400 feet tall, and the counterpoise per antenna was a 400-foot wire buried in the ground every 5 degrees of abscess.
Yes, generally, the most common number of radios to have on that gets used is some power of 2, like 16 or 32 is your best number of radios. And that's because the ground is so lost, and you can see that here. The ground is really not a very good reflector of the pattern from this antenna. So the more radios you have, the better you do that. So like if you elevate a 2-meter antenna and you put, say, 4 aluminum rods to simulate a ground plane, that actually works pretty well. What I have for my satellite antennas are 2 egg beaters, and they have the 4 aluminum rods for each one. And it works pretty well. It makes me hard to work a repeater because I have nulls in the lower part of it, but it's fine for working satellites where I'm using high elevation work.
Any other questions or comments? Because I think we should close this one down. The recording is going to be a long one, but it's very, very informative, very cool.
Well, I'm sure there'll be other questions, and I'm happy to take them.
Scott, do you think it would be worthwhile in the future to do a presentation about the basic differences of cosine for a horizontal versus a sine for a vertical antenna for lobe structures?
I don't know. Most people don't want to get into that level of detail, although I do think it is useful to understand that. It gives you a chance to, if you will, look at your results and decide whether they're sniff okay.
Scott, Diego had a question. What's the frequency for the satellite links that you're making?
You can refer to any of the AMSAT information, but I usually do 440 up, 2 meter down, 2 meter up, 440 down.
So I'll ask you a similar, what's your favorite satellite to communicate on nowadays?
Oh, I don't do it much nowadays, but I still have the antennas up. I blew up the rig that I use for that. I'd have to buy me an Icom 9700 or something to get back onto that satellite stuff. That's a long story. But
before you shut this down, Jim, I would like to congratulate Scott, you, Jim, and Dave, our president, for coming up with such a wonderful meeting for 68 participants. And we've had a lot of good business done today. This is done so well that it might become habit forming. I still think we would miss the fellowship of getting together at the Salvation Army, but for the conditions that we have to live under, this has been wonderful. Thank you very much.
Thank you, Michael.
Thank you, Michael. The thing here is the board meeting went so well this last time over Zoom here. It was so much less hassle for all the board members. We're definitely doing the board meeting via Zoom going forward, unless the board decides to not do that. I mean, it worked just spectacularly well.
Great. Does that mean I have to buy my own donuts now?
Gary had a whole bunch of them. Gary, can you share those donuts again? We'll just grab a couple.
That's a great background.
There's a bunch left, so help yourself.
Those are my favorite kind too, the glazed. I love those. You can. Why don't you mail those to me?
Let me see. Do I have any other virtual background that I can show here? No.
Okay, I think
I have this one.
I'm really getting impressed with Zoom the more I get to use it. Now, especially what I saw the day, Jim.
yeah,
I'm going to have to do a lot of work and learn how to be a real good host, though.
yeah, it's still a lot of learning, but we're doing decent enough. I really like the platform. It seems to be really stable. Well, I'm going to go ahead and close out the recording, but we can still continue on talking and things. We can
I
keep
got to cut.
going for 24 hours. Okay, stopping the recording.